Hi, I'm Pat Kelly. Okay, and in this problem, they give us the differential equation, they give us a point, and they also give us this slope field. And we're asked to do three things. First thing is to use the slope field to draw two solutions to this differential equation, and one of those is supposed to pass through that point, 0, 0. Second thing we'll do is actually solve the differential equation. The third thing we'll do is use a graphing utility just to compare our solution to the one that we're going to try to draw freehand, see how they look. So the first thing I'll do is use my slope field, and I'm going to draw two of these solutions. And I'll start with the one that passes through the point. And it really comes down to the thought process of how to draw a solution using the slope field. With all these little line segments, they're supposed to be shoving you in one direction or the other. So you're just kind of trying to go with the flow. So if I'm starting with that point, you can see my segments actually are horizontal right at x equals 0. So I am going to have a little bit of a behavior like that, horizontal tangent line. But then the rest of the flow, when I start moving away from that point, is going upward in either direction, either side. So I'm going to start going up. And then you can see the line segments are kind of steering me that way. If I stay on the right side here, they're steering me that way, and all of them start to even converge here. So I'm going to try to follow their lead and end up going like that. And I'm even going to maybe predict that that looks like an asymptote. That's what all those sloped segments are telling me. And on the other side of the y-axis, I'm again just trying to follow the flow, go with the flow. And they're heading me up in that direction and have that same kind of direction along the horizontal there, like that. This is just an approximation, we're eyeballing it, but I like that solution following the slope field going through that point 0, 0. They also tasked me with drawing another one, which I'm allowed to choose whatever I want in terms of where to start. And I'd really actually like to show you one if I picked a different point completely, like maybe even way out here. But the problem would be if I started there, that flow is going to shoot me way down very rapidly. I'm going to be off the graph, actually by quite a distance. So let me try to keep it tighter so we can see what's going on, and maybe just pick a point there. It's an arbitrary point. And then from that point, you just want to again try to follow the pattern of those sloped lines, those segments. So from that dot, you can see that I have that downward and then over direction. I'd probably follow that there. On the other side, from the other side of that point, I'm going to be going up, and I have those horizontals. I'm going to go up, level off, and then follow these segments downward and over. And I'll suggest that that might look like a decent second solution to the differential equation. Okay, now to be more exact, they want us to solve this differential equation. So I'm going to look at my differential equation and think about separation of variables. So I want to get all the y's on one side and all the x's on the other. So this parentheses here, 6 minus y, I'm going to keep it whole and divide over. When you're separating x's and y's on either side here, make sure you're using multiplication or division and not addition or subtraction. So I'll divide over the 6 minus y. While I'm doing that, I'm going to multiply over the dx. So this is what we're shooting for with separation of variables. All the x's on one side, including the differential element, all the y's on the other. Now we're going to solve that by integrating each side of the equation. One of those golden rules in mathematics is you can do whatever you want as long as you do it to both sides of the equation. Now we just have to actually do the integration. On the left-hand side, it's actually one of those logarithms. It's going to be minus, because the y is negative, absolute value of 6 minus y. On the right-hand side, a bit friendlier, is just the integral of x. So x squared over 2. And that's where I'll tack on my constant. Now looking to solve this for y, the next step I'm going to take is first to get rid of that minus sign. I'll just throw it over on the other side. I'll multiply it over. But I'm also going to change those absolute values to just parentheses. I don't want you to think I'm cheating there. If I think about the expression on the inside of the absolute value bars, 6 minus y, my specific y value is right there for this initial condition. So I'm going to look ahead and see that if y is 0, 6 minus 0 is 6, which is positive, and the absolute value doesn't do anything. So I'm just going to replace it with parentheses. And on the other side, I did throw the minus sign over. And if you've been doing a few of these, don't get hung up on those constants if you're worried about that being a minus sign there. It's just a different constant, so we might even call that C1 if it helps. I'm trying to solve for y. Okay, so then we're going to raise each side of the equation as a power of e. On the left-hand side, it just frees the 6 minus y from the natural log. On the right-hand side, we would actually have e raised to that entire expression as a power. I'm going to simplify that a little bit too with this plus c in the exponent. It's really just a coefficient in front of the e, which again can bother people, but what it comes down to is that this actually was like a C2, and this C then is a different C. Okay, it's just a constant. One last step here to get y alone. If I were to throw the y on the other side and then subtract over, 6 minus c e raised to the minus x squared over 2 power. Okay, so what that gives us is our general solution to this differential equation. We want to get the particular solution by using this initial condition. So I'm going to grab this general solution and just use our specific x and our specific y. So I'll do a quick rewrite of y equals 6 minus some constant that we're going to solve for, e raised to the minus x squared over 2 power. And then we'll plug in the 0 for y, 6 minus c that I'm looking to solve for, e raised to the minus 0 squared over 2. No need for a calculator, that's just going to be 0. E to the 0 power, which is just 1, so 0 equals 6 minus c, and finally c equals 6. What that tells me then is my particular solution is my general solution with this value of c in 6 in for c, e raised to the minus x squared over 2 power. So that's the second part of this problem, is to find that particular solution. And the third part is to use a graphing utility to kind of compare. Now we have something specific to put into our graphing utility, and we're going to see how close we got on our first approach with the slope field. Okay, so I'm going to grab my graphing utility and walk you through it. And so what I'm going to enter under y sub 1 is this function, 6 minus 6 times e raised to a negative x squared divided by 2. I'm going to go ahead and graph that, but I'll give you some advice on the window settings, especially if you want to match that slope field that we started with. I'm going to go to window, and as a min, I'm going to use -5 for x. Max for x, I'll use 5. Scale can be 1. The y min, I'm just going to go to a -1. Y max, I'm going to go to a 9, and I'll keep the scale at 1. And if I graph that, then there, remember from our original slope field, this was my blue, and it doesn't look too bad. I think we did all right with that one. Okay, so hopefully that helps. Thanks very much.